Hey everybody, welcome back to day 2, chapter 14. So hopefully you were able to get a handle on Voltaic cells from yesterday. We're going to review them again today. Today's lesson will just be lots of the same so that by the end of today you really have Voltaic cells dialed in. And I thought I'd start off with a quick little review of the vocabulary terms from yesterday. So we've got a list on the right hand side, and on the left are all the vocab terms. So what is the term for contains two electrodes and an electrolyte? Contains two electrodes and an electrolyte would be a voltaic cell. Okay, second one, aqueous electrical conductor. So in solution, or a solution that conducts electricity. And key term is electrolyte. Electrode that gains electrons. So if it gains electrons, it is the oxidizing agent gaining electrons, undergoing reduction. On a voltaic cell or a battery, we call it the positive terminal. So the positive terminal is always the cathode. Okay, and here's the opposite, the electrode that loses electrons. So this is the half cell that is the reducing agent, losing electrons and undergoing oxidation, and it's always labeled with a negative sign for the negative terminal. So cathode is the Auger, anode is Rayleigh. Okay, rate of flow of charges past a point measured in amps. So that's our electric current. Okay, so we've cleaned off the top half. Now we'll do these last four. Okay, so we've got a primary cell, a fuel cell, and a secondary cell, three different types, and hopefully you remember the difference between those three. So primary cell is your throwaway batteries, so we call it a one-way reaction. They're spontaneous. You cannot recharge them. You toss them out when they're done. The rechargeable ones are your secondary cells. They can be recharged. You can reverse the spontaneous reaction. So what's the definition of a fuel cell? It is produces electricity and you need to continuously supply. So our last definition would be potential difference, the energy difference per unit charge measured in volts. Okay, little review from yesterday. Now, this is also review, not in your notes. So just take a look at these. I've got the three different setups for voltaic cells. So the simplest one, which is a common electrolyte, and you can see that in the cell notation. We have a copper anode, a silver anode, and they are solid bars. And then here's our one common electrolyte. Not a very good design. We don't really use them in the lab because you can't separate out the two half cells. So a better design is two separate half cells. So this one is separated with a salt bridge. And you can see that in the cell notation. We have a copper anode, a silver anode, copper electrode, silver electrode. And then we have a copper 2+ electrolyte and a silver 1+ electrolyte. And the key part of that notation is right there. They are separated by a porous boundary or the salt bridge, two vertical lines. This voltaic cell is also two half cells, half cell, half cell, also separated by a porous boundary, PB. But the porous boundary in this case is a porcelain cup with micro pores in it that allow anions and cations to migrate through the pores just like they do in a salt bridge. Cations and anions can flow through the salt bridge and through the porous cup. They're both considered porous boundaries. So in terms of cell notation, they look identical. You wouldn't know a difference between these two until you saw the diagram to see that one is a porous cup and the other is a salt bridge. Basically, they work the same. Okay, so some questions. We just talked about cell notation. Do these cells all use the same metals? Yes, they do. Do they all use the same electrolytes? No. This one uses just an inert electrolyte, whereas the two half cell designs have two separate electrolytes. Okay, I mentioned this yesterday. In a voltaic cell, the mass of the anode usually decreases because the anode is your reducing agent. It's losing electrons. And if it's losing electrons, it's usually a metal. So for example, it could be copper. And if copper loses 2 electrons, it becomes copper ions. So our solid mass loses metal as it becomes aqueous. And that's typical of most voltaic cells. The metal anode breaks down into ions and electrons. Okay, and then remember in our salt bridge or our porous boundary, anions are moving towards the anode and cations move towards the cathode. And that's where the names anode and cathode come from. Now, the cathode usually increases in mass, and that's because it is gaining electrons. So let's pretend that copper 2 plus, or copper was our cathode with copper 2 plus. So the copper 2 plus would gain electrons and add more solid to the cathode. So if copper was the cathode, it would look like this. And if it was the anode, it would look like this half reaction. And really, it just depends on what the other oxidizing or reducing agent is. And we'll go through some examples of that on our table of relative strengths. Got it? Okay, that was your speedy review. So I'm going to go through a voltaic cell with you guys. And we're going to just go through the reactions, see if we can figure this one out. So this is in your notes, in your study guide, page 222. So if you want to flip that open, you can follow along with me. Okay, so we have aqueous zinc nitrate, aqueous cobalt chloride, zinc, and cobalt. So you'll find in most simple voltaic cells, you have the metal and the metal ion of both anode and cathode. Metal, metal ion, metal, metal ion. So let's just call this metal zinc solid, which means this one is cobalt solid. Okay, so in our electrolytes, we'll have zinc 2 plus and NO3 minus, both aqueous. And on this side, we'll have cobalt 2 plus and NO3 minus aqueous. Okay, so before we can do any of the chemistry, we need to identify strongest oxidizing agent, cathode, and strongest reducing agent, CATH, strongest reducing agent for the anode. So we need to jump to our table of relative strengths, which is, where did it go? It's hard for me to see it here. Right here. Okay. So we had zinc and cobalt. So searching on our table of relative strengths from our data book. Okay, zinc is right. Where are you, zinc? Okay, why am I not seeing it? Somebody help me out. Where is it? Camilo? There it is, thank you. Okay, zinc solid, right there. Okay, and cobalt 2 plus is right here. Okay, so cobalt 2 plus and zinc solid. So looking at those two positions, it's not going to let me mark on it very well. We can see that we have zinc as our strongest reducing agent way down here, and cobalt 2 plus as our strongest oxidizing agent up there. Okay, so zinc, strongest reducing agent, which means this is the anode. And cobalt is the cathode, strongest oxidizing agent. Now, students always get confused here because they're like, well, wait a minute, it's the cobalt 2 plus that's the strongest oxidizing agent. And that's true, but we still label its electrode as the cathode because we always need a solid cathode. So plus sign for cathode, even though this is our strongest oxidizing agent here, we label its electrode as the cathode. So zinc is our anode with a negative sign. Okay, now we can figure everything out. So our oxidation half reaction is the cathode, which is the cobalt 2 plus. I said that wrong, so that's reduction half reaction is the oxidizing agent, gaining electrons and undergoing reduction. So cobalt 2 plus gains 2 electrons and becomes cobalt solid. Oxidation half reaction, our Rayleigh reducing agent lose electrons oxidation is the zinc solid losing 2 electrons and becoming zinc 2 plus. Okay, there's our half reactions. We could add them up and get our net reaction. Zinc solid plus cobalt 2 plus gives cobalt solid and zinc 2 plus aqueous. Okay, is it spontaneous? Yes. The oxidizing agent, the cobalt 2 plus, sits above the reducing agent zinc. Okay, now we need to do some labeling here. So we've labeled cathode, anode, direction of flow of electrons. So the symbols help us. This one's a negative anode and a positive cathode. Or look at the half reactions. The cathode is gaining and the anode is losing. So if I throw some electrons in here, the cathode gains and the anode loses. Okay, last things we need to do are ions in the salt bridge. I'm going to put a plus sign for cations and a minus sign for anions. Cations go to the cathode, anions go to the anode. It's that simple. Salt bridge. Okay. Beauty. If you have to draw one, this is the best way to draw them. Just a nice simple diagram like that. And make sure the salt bridge is down inside the electrolyte. Sometimes students have them floating up in the air, but it actually needs to be in the electrolyte to complete the circuit. As negative electrons go to the cathode, positive cations go there to keep it neutral. And same thing on this side. We are losing negatives, so we are gaining negatives to replace those that are lost to keep it neutral. This thing only works when neutrality is maintained, and that's why the ions are flowing. Okay, hopefully no questions on that. This is something you'll be asked to do on your assignments, is draw and label. Predict the two half reactions, draw and label everything. Okay, so that's a bit of a review for you. Now we're going to add a little bit more material to it. Voltaic cells with inert electrodes. Okay, what does inert mean? Think. Does not react. Okay, so why would we want electrodes that do not react? Well, here's why. For metals and metal ions, you can always use the metal and its ion because the metal doesn't react with its own ion. It says that right there. The metals won't react with their ions, so you're not going to get some weird spontaneous reaction happening inside the half cell. Okay, we don't want a half cell to react with itself. We want it to react with the other half cell to give us a complete redox reaction. So if you have an oxidizing agent or a reducing agent that is not a metal, okay, it's not a metal or a metal ion, then you have to use an inert electrode. So for example, if we were going to be using acidic dichromate or hydrogen gas, there is no metal form of acidic dichromate, and there's no metal form for hydrogen. These are non-metals without metal electrodes. So when you have non-metals as your reactants, you need to use inert metal electrodes that won't take part in the reaction. And the only two we worry about in Chem 30 are these guys, carbon and platinum. So if you see electrodes made of carbon or platinum, you know that those are inert. And the reason we're using them is because the reactants don't have a metal form. So let's take a look at our cell notation for a practical example. Okay, we're using carbon. It's inert. Why are we using carbon? Because we have iron. I just got to make sure that's all right. This is our reducing agent losing electrons. Okay, so we have iron 2 plus turning into iron 3 plus. We don't want it to go to iron metal because this is our reducing agent losing electrons. Over on the other side, we have acidified dichromate, which also does not have a metal form. So we have to go with an inert carbon electrode. So on this one, the Cr2O72 minus and the H plus is gaining electrons. So that's our cathode oxidizing agent. And this is our anode reducing agent. And the actual reducing agent is the iron 2 plus that is turning into iron 3 plus. So that's why we aren't using iron. If we used iron solid here, then it would be the reducing agent and lose electrons and become iron 2 plus, and that's not the reaction we're interested in, so we can't put iron in there. We want to force iron 2 plus to turn into iron 3 plus, so that's why no iron, carbon instead. And on this side, there is no metal, so carbon instead. We could also use platinum as well. So what would this full reaction look like? What would the cell look like? That's on the next slide.